72 hours ago, the European Space Agency presented what they called the closest look at the three-eyed Atlas. This interstellar object captivates and frightens the world. Billions of dollars in space technology, 7 orbiters around Mars, ready to capture a unique moment. And what did we get in the end? A blurred white dot as if someone sneezed on the camera lens, and moments later, social media exploded. Not from admiration, but from anger. Amateur astronomers with telescopes in the yard obtained clearer images of comets millions of miles away. And yet NASA, with its orbital reconnaissance craft for Mars, equipped with the most powerful camera ever sent to another planet, remained completely silent. The justification for the government's closure? It begins to sound unconvincing, especially when you realize that the Chinese and UAE orbiters are also mysteriously silent. By the time you finish listening to this, the three-eyed Atlas will be less than a week from disappearing behind the sun, hidden from all telescopes on Earth at the moment it should be most active. And if the Harvard physicist Avi Loeb is right, what happens next could change everything we thought about possibilities in our cosmic neighborhood. If this mystery captivates you as it does me, like and subscribe to stay updated as this story unfolds in real time. Write in the comments where you are listening from, what time it is, and whether you think we are being told the whole truth about the three-eyed Atlas. If you want to help our community grow, share this on social media or your favorite messenger. Thank you for always supporting us. Chapter 1. The Photo That Broke the Internet. The 7th and 8th of October, 2025 will be remembered as the moment when the space community collectively lost patience. We had been preparing for this for several months. The three-eyed Atlas, the third confirmed interstellar object ever discovered in our solar system, was approaching Mars. 7 different spacecraft from 4 space agencies were ready to capture unprecedented images. Expectations were high. Scientists promised us clarity, answers, perhaps even proof of what this object was. And then, the images were published. The ExoMars Trace, gas orbiter of the European Space Agency, being only 30 million kilometers from the three-eyed Atlas during its closest approach on October 3rd, released a series of images that can be described as deeply disappointing. A blurred white dot slowly moving across a field of stars, devoid of details, structure, or anything that could help understand whether we are looking at a natural comet or something much stranger. The response was immediate and brutal. Astronomy Vibes, a popular account about space on X, published a comparative image that went viral within hours. On one side, a clear, detailed image of Comet Lehman taken by an amateur astronomer with a simple mirrorless camera. On the other side, an image of a three-eyed Atlas from the European Space Agency. The caption read, "If a simple mirrorless camera can capture the Lemon Comet, why can't NASA catch a three-eyed Atlas passing close to Mars?" At this moment, this post has gathered over 40,000 shares, and that number continues to grow. But it was the subsequent message that caused a real stir. Billions in funding, and these are the best photos they could provide? It looks more like a weather balloon in a foggy backyard. To understand why people are so outraged, we need to figure out what we expected and what we ultimately received. The Cassis camera, mounted on the ExoMars Trace gas orbiter, has an angular resolution of 11.36 microradians per pixel. At a distance of 30 million kilometers, this corresponds to 340 kilometers per pixel. For comparison, the estimated nuclear size of the three-eyed Atlas ranges from 5 to 46 kilometers in width. This means that the entire solid core of this object will occupy, at best, only a fraction of a pixel in these images. But here is where it gets interesting. The European Space Agency knew about this from the start. They understood that their cameras were meant for capturing the bright Martian surface from a distance of just a few hundred kilometers, not for observing dim objects located tens of millions of kilometers away. Nick Thomas, the lead researcher of the Cassis camera, acknowledged this in an official statement. It was a very challenging observation for the instrument. The comet was 10,000 to 100,000 times dimmer than our usual targets. So why publish images that they knew would be inadequate? Why create expectations for several months, only to provide material that offers no new information? The official version is that they published what they had, and that these are the best possible images from the available equipment. But the timing seems deliberate, almost like an attempt to distract attention, give people something to look at, while the real data remains hidden. Because we must not forget, there are better images, Much better. And they are concealed. Chapter 2. The Missing Crown Jewel. While the European Space Agency published blurry dots, NASA's Mars Reconnaissance Orbiter captured entirely different images. The high-resolution camera, short for high resolution, is the most powerful camera ever sent to another planet. Her resolution is so precise that from Mars's orbit she can distinguish objects the size of a table on the Martian surface. When the three-eyed Atlas approached Mars on October 3rd, the resolution was about 30 kilometers per pixel at the object's distance. This is more than 10 times better than what the European Space Agency cameras managed to capture. If there are any structures, unusual features, or anything that doesn't fit the natural narrative of the comet, the high-resolution camera will see it. Avalov, a physicist from Harvard who has been tracking the three-eyed Atlas since its discovery, stated in his latest blog that the brightest pixel in the high-resolution image will provide the best data on the area of the three-eyed Atlas. We all hope that Harris's team will publish their images as soon as possible. This was written on October 7th. Now it's October 8th, and there is still no news. The official explanation is the shutdown of the United States government. More than 15,000 NASA employees, over 80% of the agency's workforce, have been placed on forced leave. The agency's website is not being updated, and public communications have ceased. This is bureaucratic paralysis at the worst possible moment. But something doesn't add up. The European Space Agency released its images. There is a European agency completely untouched by American political issues. China's orbital probe, Tianwen-1, was also ready to observe the object, three-eyed Atlas, with its medium-resolution camera. But he is silent. The UAE orbital spacecraft, Hope, equipped with a research camera, also had the capability to take pictures. Nothing. Several space agencies and sovereign states with completely different bureaucracies and priorities simultaneously cannot or do not want to present their best data about the most scientifically significant object to visit our solar system in recent years. This pattern is hard to ignore. Social media is ablaze with speculation. Some speak of coordinated actions, while others suggest that something has been noticed, requiring careful analysis before publication. More conspiracy-minded individuals claim that the images show something so anomalous that releasing them without proper context could cause mass panic. This latest theory seems absurd until one remembers what happened last week with the observations of amateur astronomers. Because while professional space agencies share their data cautiously, amateur astronomers capture images that raise more questions than they answer. Chapter 3. When amateurs see what professionals do not show. On October 3rd, the day when three eyes of the Atlas came closest to Mars, a Portuguese astronomy enthusiast with the nickname Dobsonian Power uploaded an image that instantly went viral. Using only a solar telescope from his yard and aggressive digital processing, he captured what appears to be an angular structure within the three eyes of the Atlas. Dark geometric shapes protruding, not conforming to the typical diffuse light of a comet's nucleus. The caption he added was simple yet meaningful. What the hell is this? For 6 hours, the image spread across all major astronomy forums, subreddits, and social networks. The reaction quickly split into two groups. One side saw clear evidence of artificial structures, confirming that the three eyes of the Atlas is not what mainstream science believes. Another group dismissed this as classic pareidolia, the human tendency to see patterns where none exist, exacerbated by artifacts from inappropriate equipment. The opponents had strong technical arguments. Solar telescopes use specialized filters designed for observing the extreme brightness of the sun, not for faint deep space objects moving at stellar speeds. The equipment was simply not intended for such observations. If you add aggressive digital enhancement to compensate for the shortcomings of the setup, you are essentially asking the algorithm to invent details that do not actually exist. This is similar to enhancing a blurry photo to the point where faces begin to emerge from the noise. But this is where the story becomes complicated. Dobson's Power is not some random internet conspiracy theorist with a cheap telescope and an overly vivid imagination. He is a respected astronomy enthusiast who has been sharing real astrophotographic works for over 10 years. His channel on the video sharing platform contains meticulous documentation of his equipment, methods, and image processing workflows. This is not someone who tries to fabricate evidence for clicks, and when asked about the strange structures in the three-eyed image, he did not insist on his claims. Instead, he acknowledged the presence of uncertainty. He promised to try again when the object becomes visible from Earth in early November after passing behind the sun. His response was scientific and cautious, making his reaction to the image even more significant. Within 24 hours, several websites published articles specifically debunking his CAPTCHA. Amateur telescope tricks. A strange image from three eyes. Here's why it's not what it seems. The timing felt coordinated. The tone was defensive, as if someone was eager to quickly establish a narrative that nothing unusual had been recorded, and that all possible anomalies were merely technical artifacts before the image drew too much attention. And then, the war of enhancements began. Users across the internet began uploading original images from the European Space Agency and processing them with their algorithms. Some used standard methods for stacking astronomical images. Others used artificial intelligence tools to enhance low-quality photos. Some descended into complete chaos, employing machine learning models trained to restore fine details from limited data. The results varied. Some showed only slightly clearer versions of the same blurriness. Others revealed visibly clear geometric patterns, edges, and structures that seemed too regular to be natural ice or stone. The problem is that as soon as you start aggressively processing an image, especially with AI tools, you no longer look at what truly exists. You look at what the algorithm thinks should be there based on its training data. If you train artificial intelligence on thousands of images of spacecraft and then ask it to enhance a blurry object, it might create details resembling spacecraft because that's what it has learned to recognize. This is a scientific dead end wrapped in an illusion of clarity. But the spread of these improved images had an unforeseen effect. They confused the situation so much that distinguishing between genuine observations by enthusiasts and pure fakes became almost impossible. Within 48 hours of the publication of the European Space Agency's photograph, dozens of so-called enhanced versions began circulating on the internet. Some depicted metallic surfaces, while others resembled solar panels or antennas. There were even options with blinking lights and visible engines. Most of these images were obvious forgeries created by people with too much time and Photoshop skills. However, among this noise, a few images looked different, more restrained, less sensational. They exhibited a sufficiently unusual regularity to wonder if something real was hidden behind the flow of obvious forgeries. Chapter 4. 4 Channels That Will Not Disappear. On October 4th, an anonymous user on a paranormal forum published information he called Insider about the three-dimensional Atlas system. The post was simply titled Data Leak ESA and began with a statement about qualifications that sounded convincing enough but left anonymity. I am a doctoral student working with the European Space Agency and have constant access to the combined observational data of the three-dimensional Atlas system. Leaks on the internet are a common phenomenon. Most are easily dismissed as fictional stories or blatant trolling. But this case was different. The level of technical detail was concerning. The author did not make insane claims about alien invasions or secret military operations. Instead, he outlined a series of specific observational anomalies that, if true, would radically change our understanding of what a three-dimensional Atlas system is. The first anomaly is chemical impossibility. According to the post, spectroscopic analysis shows that the three-dimensional Atlas system emits about 100 kilograms of nickel gas per second, but almost without ionic radiation. In normal stellar and planetary chemistry, nickel and ions are inseparable twins. They form together during supernova explosions, travel together through interstellar space, and meet together in comets and asteroids. Finding abundant nickel with almost no ions is like discovering smoke without fire. This contradicts the basic assumptions about how matter behaves in natural cosmic conditions. The second anomaly is a thermal contradiction. The object emits a massive amount of gas and dust, a characteristic sign of an active comet heated by the sun. But infrared observations show that it remains cold, much colder than it should be considering its gas emission rate and proximity to solar radiation. The author of the post compared it to watching a person sweating in a freezer. The physics does not match the observations. The third anomaly is the accuracy of the trajectory. The post mentioned that Avalov publicly stated, the three-dimensional Atlas system came with an orbital tilt of only 4.89 degrees relative to the plane of the Earth's ecliptic. However, the author on the 4 channel added something more important, but did not emphasize it. The trajectory is not just unusual, It is a perfect straight line towards the galactic core, without hesitation, deviation, or signs of gravitational disturbances from nearby stars. This object had been moving through interstellar space for millions or even billions of years, as if it were aimed. Then came the part that elevated this assumption from an interesting speculation to something darker. The poster claimed that the object matched the profile of what they called a post-biological entity, not a natural comet, not an ordinary spaceship, something in between. They described it as having a three-phase partial engine with an estimated power of 75 megawatts, which continuously transmitted an active signal and, according to them, explored our solar system. The post ended with a theoretical framework. The author suggested that the three-eye atlas could be a macroscopic quantum object, specifically a kind of billiard ball. This is an exotic theoretical construct from the field of particle physics, a type of non-topological solid body that could theoretically exist on scales much larger than subatomic particles. If stable, such a sphere could possess properties that seem impossible within the realm of conventional physics. It could be incredibly dense while remaining sparse. It could instantly absorb and redistribute energy throughout its structure, which would explain the thermal contradictions. This could also explain the problem with nickel without iron if the internal quantum state of the sphere preferentially produces certain isotopes. For 18 hours, the post was screenshot and spread across Reddit, Twitter, and specialized UFO research forums. The thread on the subreddit about conspiracy theories gathered over 2,000 comments before the moderators locked it for violating rules regarding unverified claims. However, the lock did not stop the discussion. It simply moved to other platforms, fragmenting into dozens of parallel discussions, each directing the original post in different directions. Some focused on chemical anomalies, others on the billiard ball hypothesis. Some began to link this to earlier claims that the three-eye atlas could potentially be the source of the WOW signal recorded in 1977. On October 4th, NASA's Perseverance rover, located in the Jezero crater on the surface of Mars, recorded something in the night sky. The image from its right navigation camera showed an elongated strip of light, approximately 4 times longer than its width. At first glance, it looked like a typical long exposure of a moving object. Comets and asteroids often appear smeared in images when the camera tracks the stars instead of the object itself. This is a standard situation. However, mathematics did not confirm this assumption. When people began to calculate the apparent length of the strip based on the known characteristics of the Perseverance camera and the distance to Three-Eye Atlas at that moment, they received a disturbing number: 50,000 kilometers. This is not a comet's core. It's not even a comet with a tail. It's something entirely different. In comparison, the diameter of the Earth is less than 13,000 kilometers. If this trace reflected the actual physical size of the 3 moons of Atlas, we would be dealing with something almost 4 times wider than our planet. Social networks exploded with speculation. Was the three-eyed Atlas really a huge cylindrical apparatus? Perhaps it concealed its true size and shape behind a hazy cloud of gas and dust? The moment felt significant. This photo appeared just a day after the flyby of Mars, when all professional space agencies unexpectedly fell silent. Some saw this as confirmation that something anomalous had been captured, something that defied simple explanations. Speculations reached such a level that Anna Luna, a Congress member known for her interest in unexplained aerial phenomena, directly approached Avi Loeb for his analysis. Think about this for a moment. A member of the United States House of Representatives felt the need to contact a physicist from Harvard regarding a photograph from Mars. This is not common practice. This indicates that someone in official circles was sufficiently concerned to seek expert opinion outside the usual NASA communication channels. Loeb's response was detailed and, at first glance, reassuring. He calculated that the Perseverance navigation camera has an angular resolution of 0.33 milliradians per pixel. At a distance of 3 astronomical units, when the photograph was taken, approximately 38 million kilometers, this translates to 12,500 kilometers per pixel. The trace in the image covers about 4 pixels, resulting in a length of 50,000 kilometers. However, Loeb argued that this was an artifact of composite imaging. The trace did not show the actual size of the 3 Atlas. It displayed the path that the object left on the Martian sky over a long integration time, likely around 10 minutes of stacked exposures. His reasoning was sound. Mars orbits the Sun at a speed of 24 kilometers per second. Three Atlas spacecraft move at 67 kilometers per second relative to the Sun in the opposite direction, resulting in a relative speed of over 90 kilometers per second compared to Mars. In 10 minutes, this amounts to exactly 54,000 kilometers of travel, perfectly matching the observed length of the trail. The shape was not an object, it was the movement of an object, smeared over time. The case is closed, right? The theory of the cylinder was debunked by basic physics and thorough calculations, but Loeb included one sentence in his analysis that conspiracy theorists grabbed onto like a lifebuoy. He wrote that if the images from the navigation camera are single frames with an exposure time of less than 328 hundredths of a second, then the brightness and angular length of the observed source imply that it is not three Atlas moons. In that case, the source could be much closer to the camera, allowing it to blur into an elongated image with smaller spatial dimensions and speed. Wait, if these are single frames, then what kind of photograph is Perseverance if it wasn't 3I Atlas at all? It was something else, something closer to Mars. This qualifier opened a door that no subsequent explanations could fully close. Since NASA did not confirm whether the images were composite or a single frame, they did not publish the metadata. Neither the duration of exposure nor the number of superimposed images was specified. The reason for this was also the government shutdown. There are no employees to process requests, and no one can confirm the basic technical details of how this image was made. Chapter 6. 48 Years of Silence. On August 15, 1977, the Big Ear radio telescope, owned by Ohio State University, recorded 72 seconds of radio wave energy that was so unusual and perfectly structured that astronomer Jerry Amon circled it on the printout and wrote one word in red ink: wow. For nearly 5 decades, this signal remained one of the greatest mysteries in the search for extraterrestrial intelligence. It came from the direction of the constellation Sagittarius, near the Delta Star field. The signal had a narrow bandwidth and was focused on one specific frequency, and it never repeated. Hundreds of subsequent observations, thousands of hours listening to the same region yielded no results. Only this single burst 48 years ago, and then eternal silence. Until Avalov calculated the object 3I Atlas, he determined where this object was on August 12, 1977, just 3 days before the signal WOW was discovered. The answer turned out to be about 600 astronomical units from Earth, which is roughly 600 times the distance from Earth to the Sun. But more importantly, he calculated the direction from which the 3 Atlas stars were moving at that time. Right ascension, 19 hours 40 minutes, declination minus 19 degrees. The signal, WOW, came from a direct descent at 19 hours 25 minutes, with a declination of minus 27 degrees. These two directions are separated by about 9 degrees. In the boundlessness of space, where random objects can come from literally any direction, the probability of such a coincidence is about 0.6%. It's not impossible, but raises deep suspicions. Loeb did not stop there. He asked the next logical question. If 3 AIs sent a signal, WOW, from a distance of 600 astronomical units, how powerful must the transmitter be? The mathematics here is simple. The detected intensity ranged from 54 to 212 Janskys over a 10 kilohertz bandwidth. At a distance of 600 astronomical units, this corresponds to a transmitter output power from half a gigawatt to 2 gigawatts. For reference, a typical nuclear power plant on Earth produces about 1 gigawatt, so we are talking about energy levels comparable to a nuclear power plant, concentrated in a narrow beam. It is not impossible for an advanced civilization. It makes sense if you are trying to send a signal that can be detected over interstellar distances without wasting energy on multi-system broadcasting. There is another aspect that makes the connection to the signal more significant. The WOW signal was detected at a frequency of 1420.4 MHz, with a blue shift of about 10 kilometers per second towards Earth relative to the hydrogen line, indicating the source is moving towards us. Object 3I Atlas is currently approaching the Sun at a speed of about 60 kilometers per second. Loeb suggests that if this object had maneuverability, it could have moved slower in 1977 and then accelerated after detecting planets in the habitable zone of our solar system, sending a reconnaissance pulse, a radar scan checking for signs of technological civilization before approaching. This is what makes this connection so disappointing. Checking it would be extremely simple. Point the radio telescope at Triangulum Atlas. Listen to the hydrogen line frequency. If it transmits a signal, we will know within hours. If silence, then the connection with the wow signal is likely coincidental. A simple test, a clear answer. Yet as Loeb noted in his latest blog, no radio telescope reported data on Tri-Eye Atlas. A very large array did not conduct observations. The Arecibo telescope is destroyed. The Green Bank telescope has not published observations. Even SETI, an organization literally dedicated to the search for extraterrestrial signals, has not announced any monitoring efforts. The silence from the astronomers' community is deafening. Chapter 7. The Path That Should Not Exist. Imagine throwing a dart at a globe from the other side of the room with your eyes closed. Now imagine that a dart not only hits a globe, but lands a few degrees from the equator. This is roughly the statistical improbability we face when considering how the Tri-Eye Atlas entered our solar system. Objects coming from interstellar space can appear from any direction. They must be evenly distributed across the celestial sphere, arriving at any angles. Nevertheless, the Tri-Eye Atlas entered with an orbital inclination of only 4.89 degrees relative to the plane of Earth's ecliptic, less than 5 degrees, placing it in less than 1% of possible arrival angles. Avi Loeb emphasizes this point in every interview, blog, and public statement since July. The trajectory is anomalous, not just unusual, but statistically highly unlikely for a random interstellar object. To understand why this is so, one must imagine how objects move through the galaxy. Stars in the Milky Way disk rotate around the galactic center at an average speed, but also have random movements up and down, sideways, like bees flying around a hive. This coincidence means that objects ejected from other star systems should arrive in our solar system with equal probability from all directions. There is no preferred direction, no cosmic highway, guiding interstellar guests into the plane of our ecliptic. And before anyone suggests that objects from the Milky Way arrive at small angles, Loeb also touched on this issue. The galactic disk is tilted about 60 degrees relative to the ecliptic plane of our solar system, which is more than 10 times the tilt of the three-eyed Atlas. If this object originated from a typical star system in the galactic disk and was ejected randomly, we would expect it to arrive at a steep angle, not a shallow one. Such alignment contradicts what galactic geometry predicts. Compare the three-eyed Atlas with other interstellar objects we discovered. Oumuamua, found in 2017, arrived at a tilt of 123 degrees, coming in steeply from above the plane of the solar system. Two Iberosov objects, observed in 2019, had a tilt of 44 degrees, still steep, still consistent with a random arrival from interstellar space. Both of these objects behaved exactly as expected from natural interstellar visitors. The three-eyed Atlas is an exception, an anomaly that does not fit into the overall picture. Loeb calculated the probability of this alignment, assuming random directions, and it was less than 1%. Some colleagues objected, suggesting that his statistics might be too conservative. Perhaps the true probability is closer to 5 or 10%, considering various selection effects and observational biases. Even at 10%, we are still talking about something that should happen only once in every 10 interstellar objects we discover, and we have found only 3. The odds that the third will be a rare exception rather than the rule are not in favor of a match. Now, add to this everything else, the alignment of the signal, wow, also with a probability of less than 1%. Chemical anomalies with nickel but without iron, thermal contradictions, the absence of high-resolution images from several space agencies, a government shutdown that occurred at the very moment when NASA needed it most. Each of these events can be explained as coincidence, measurement error, or bureaucratic incompetence. But when you start accumulating anomalies, when you begin to multiply small probabilities by each other, the cumulative improbability becomes harder to ignore. In statistics, there is a principle called the prosecutor's fallacy. It is the error of interpreting several independent low-probability events as related when they are actually just random coincidences that have grouped together by chance. If you flip a coin enough times, eventually you'll get 10 heads in a row. This doesn't mean the coin is rigged, it just means you've flipped it enough times for unlikely sequences to occur. Skeptics will argue that what we observe with the three-eyed Atlas is a natural comet, which accidentally has several unusual, yet ultimately explainable properties that coincidentally appeared together in one object. Unlikely, of course, but not impossible. However, the counter-argument is equally valid. If something walks like a duck, quacks like a duck, swims like a duck, and has duck DNA. At some point, you must consider the possibility that it is indeed a duck. Or, in this case, if the object appears on a statistically unlikely trajectory, demonstrates chemical signatures that do not correspond to natural processes, correlates with an unresolved radio signal that has existed for 48 years, and causes several governments to conceal their best visualization data, it may be worth seriously considering that we are dealing not with an ordinary chunk of ice and rock from another star system. Chapter 8. When questions become dangerous. Something strange began to happen around October 5th. Users on various platforms started reporting that their posts about the three-eyed atlas were disappearing. They were not marked as false information, they simply vanished. One of the Reddit users documented a detailed post analyzing the chemical anomalies revealed in the alleged data leak from the European Space Agency. This post quickly gained popularity, gathering hundreds of votes in favor, and dozens of comments in just 2 hours, then disappeared without any explanation from the moderators. It was simply deleted. When the user tried to post it again, the submission failed, and he found himself in a shadow ban without notification or explanation. On Twitter, now X, several accounts noticed similar trends. The Astronomy Vibes account, which went viral due to criticism of ESA photos, reported a significant drop in engagement after October 7th. Posts that usually reach tens of thousands of views suddenly stalled at just a few hundred. No official restrictions, no warning messages, only algorithmic suppression, sufficient for denial, yet aggressive and effective. Other content creators in the astronomy community have also noticed similar issues. Videos about the three-eyed atlas, which usually had good popularity, began to receive only a small share of their usual reach. YouTube presented another problem. Content creators posting analytical videos with assumptions about the three-eyed atlas started receiving demonetization notifications. The stated reasons varied. Some posts were marked for discussing sensitive topics without proper context. Others fell into the category of potentially misleading materials on scientific issues. Some received a blurred but threatening indication of content that may not be suitable for all advertisers. The behavior model was clear. One could create a video claiming that the three-eyed atlas is merely a commentary and that mainstream science understands everything, which was quite acceptable, with monetization and promotion. But what if there are anomalies that require investigation? Suddenly, your video becomes unsuitable for advertising. Facebook's approach was the most evident. The platform's fact-checking system, supported by third-party organizations, began aggressively flagging content about the three-eyed atlas. Posts sharing leaks with 4 channels received warnings about a lack of context. Claims of trajectory anomalies were marked as partially false, even if the post simply quoted published calculations by Evie Loeb. Fact-checking articles offered assurance. Space agencies confirmed the absence of threats from the interstellar comment. Experts claim that the unusual features are likely the result of natural processes, but the subtext was clear. Don't worry, don't speculate, trust the authorities, and move on. The timing seemed coordinated. It all intensified over the 48 hours following the publication of a photo from the European Space Agency, right in the midst of public discontent over the lack of quality images. This is the very pattern that makes conspiracy theorists feel justified, while skeptics roll their eyes in paranoia. The fact is that social networks constantly suppress content. Algorithms change. Engagement fluctuates. Fact-checkers label misinformation. These are routine platform operations, not evidence of coordinated censorship. Unless there is a clear pattern, if all this happens simultaneously, deliberately targeting one specific topic precisely when public interest is at its peak, and official responses are absent. Some creators began to use coded language to avoid suppression. Instead of atlas with 3 eyes, they said visitor or object. Instead of alien or extraterrestrial, they used unearthly or anomalous. It was like people were developing a new dictionary to discuss what platforms didn't want to be openly talked about: stress and real-time effect. The more content was suppressed, the more people assumed there was something worth hiding. The more aggressively the fact-checkers opposed, the less people trusted the official version. Each attempt to control the conversation only heightened suspicions that this conversation needed to be controlled. Chapter 9. The Moment We Cannot Observe. October 29th and 30th. Remember these dates. In less than 72 hours, the atlas with 3 eyes will reach perihelion, its closest approach to the Sun, passing approximately 202 million kilometers just inside Mars's orbit. For an ordinary comet, this is the moment of truth. Intense solar radiation at this distance should cause a sharp release of gas, possibly even fragmentation. We've seen this before. Comets approach the Sun, the heat becomes too strong, and they break apart. It's spectacular when it happens. And if the Atlas with 3 eyes is just an ordinary asteroid from another star system, that is exactly what should happen. But here's the problem. We won't be able to see it. The Atlas with 3 eyes will be on the opposite side of the Sun from Earth during its perihelion. Every ground-based telescope on our planet will be useless. The object will be hidden in sunlight, completely inaccessible for observation at the moment it should be most active and open. Some call it an unfortunate coincidence. Others see it as suspicious convenience. If you wanted to do something without being watched, you couldn't choose a better temporary window. Avi Loeb clearly outlined what would happen next. In his blog post from October 3rd, published on the day of Mars's flyby, he described 2 scenarios. If the 3-eyed Atlas is a natural comet, it may soon erupt in a gas cloud or shatter into icy fragments. Sunlight will be absorbed by its surface, releasing gigawatts of energy. This energy has to go somewhere. For ice and stone, it leads to evaporation, sublimation, possibly even structural failures. But then, Loeb proposed an alternative. If this is an artificial object, it can maneuver using the Sun's gravitational assist or release probes that can intercept Earth or other planets due to its retrograde orbit, moving in the opposite direction to the planets around the Sun. Read this again. Launch probes that can intercept Earth. He no longer speaks of passive observation. He talks about active deployment. The retrograde orbit plays a key role here. The 3-eyed Atlas moves in the opposite direction to the planets around the Sun. This means that any probe he launches will not resist the movement of the planets to reach us. It will simply be able to enter the interception trajectory and let orbital mechanics do its job. Behind the Sun, hidden from our view, it would be trivial to launch something towards Earth that wouldn't be detected until it was close. Loeb went further. He wrote, "When you look at the Sun in the coming weeks, keep in mind that the 3-eyed Atlas is passing behind it. If the 3-eyed Atlas maneuvers towards Earth when it reappears on the other side of the Sun, financial markets may collapse. Financial markets may collapse. This is not a metaphor. This is not a hyperbole." He hints that if this object demonstrates technological capabilities and changes its course towards Earth after perihelion, the economic and social consequences will be immediate and serious. Stock markets react to uncertainty. The uncertainty of a potentially hostile interstellar object actively changing its trajectory towards our planet represents an existential level of uncertainty, heightening the tension and the urgency of the situation. The government shutdown means that NASA is not operating during a critical observation period. The best images from the flyby of Mars are still unpublished. Amateur astronomers will not be able to observe the object for the next month as it is behind the Sun. The radio telescopes did not check for transmissions. We are moving blindly towards the most important moment of this meeting, and whether due to incompetence or deliberate silence, we have created a situation where we will not know what the 3-eyed Atlas will do at perihelion until it has already happened. There is a group that observes. The Galileo project, led by Loeb himself, manages 3 observatories, one in Massachusetts, one in Pennsylvania, and one in Nevada. They are equipped with high-quality cameras, infrared sensors, and radio receivers specifically designed to detect anomalous aerial phenomena. At the end of October and the beginning of November, all 3 observatories will be operating at full capacity, watching the sky for something unusual. If the 3-eyed Atlas releases probes, and if increased activity of unidentified aerial objects is recorded during its perihelion, Galileo's instruments may capture it. Maybe is the key word, as 3 observatories cover only a small part of the Earth's celestial sphere. And if something passes by these specific observation zones, we will completely miss it. Chapter 10. What will happen next? Early November. At that moment, the 3-eyed Atlas will emerge from behind the Sun and become visible from Earth again. Ground telescopes will track it once more. We will see if it survived perihelion or was destroyed by solar pressure. We will measure its trajectory to determine if any adjustments were made and finally find out if 4 months of speculation, conspiracy theories, and uncertainty were justified, or if it was just a collective hysteria about a completely natural interstellar visitor. If the three-eyed atlas exits on the same trajectory it entered, showing clear signs of fragmentation or increased gas emission corresponding to solar heating, and behaves exactly like the two-eyed Borisov during its solar approach in 2019, then the mystery will be nearly solved. This is a natural comet with unusual chemistry, statistically unlikely trajectory, but ultimately just an icy remnant from another star system passing through ours. The connection to the WOW signal will turn out to be a coincidence. A leak on the forum will become a creative fabrication. The lost NASA images will turn into bureaucratic delays during the government shutdown. Everything will return to normal, where interstellar objects are interesting but not alarming. But if this is not the case, if the three-eyed atlas emerges with a changed trajectory, if it demonstrates even slight course corrections that cannot be explained by gas emissions, if radio telescopes finally focus on it and capture structured transmissions, if high-risk NASA images ultimately appear showing geometric structures that should not exist on a natural object, then we will find ourselves in completely uncharted waters, not only in scientific terms but also socially, politically, and economically. Every assumption about our place in the universe will be questioned, and every government reaction to the issue of contact with extraterrestrial civilizations will be scrutinized in real time. Avalov created what he calls the Loeb scale. It is a ranking system that shows how likely it is that an object is artificial and what potential threat it poses. Rank 1 means almost certainly a natural object with interesting but explainable anomalies. Rank 10 clearly indicates an artificial object with proven hostile intentions and the ability to reach Earth. It publicly stated that it would not rate the three-eyed atlas below 2, even in the best scenario. The anomalies are too persistent, too numerous, and too interconnected. Rank 2 indicates that the object is likely natural, but has enough unexplained features to warrant serious investigation. It means we cannot definitively rule out artificial origin without further data. At this moment, we are in a state of uncertainty, balancing between a possible natural object and a potential technological artifact, waiting for November, waiting for high-quality images that may never arrive, waiting for radio observations that have yet to occur, waiting for the three-eyed atlas that will either continue its hyperbolic path beyond the solar system, never to return, or do something that will force us to confront the reality. We are not alone, and we are not ready. The European Space Agency announced that their spacecraft JUICE, exploring the icy moons of Jupiter, will observe a three-eyed atlas from November 2nd to 25th, using various instruments. This will happen right after perihelion, when the object should be in its most active state. Data will not be available until February 20th, 2026, due to communication delays and processing time. 7 months of waiting for images taken in November. 7 months of uncertainty about whether the increased activity observed by JUICE is a normal cometary outburst or something entirely different. 7 months of questions about whether the blurry spot shown to us by the European Space Agency in October was truly the best they could offer, or if they were cautiously managing the disclosure of information they didn't know how to communicate. Whatever the three-eyed atlas may be, its discussion has revealed something important about our civilization. We do not trust our institutions when it comes to something so significant. We do not trust official assurances. We see patterns in the timing of outages and data delays that may be real or may not be. We are ready for conspiracy theories because we've learned, sometimes from our own experience, that a conspiracy is not always a theory. Sometimes it's just early information that later proves to be fact. Chapter 1. An invisible visitor. On the first day of October in the 25th year, something the size of a giraffe passed between Earth and our satellites. It came closer to our planet than the orbit of the International Space Station. We had no idea of its approach. By the time the astronomers noticed it, asteroid 2025 TF had already slipped back into the darkness of space, like a shadow that forgot to announce itself. Think about this for a moment. We live in an era where we can photograph distant galaxies formed billions of years ago, but a stone close enough to nearly graze our atmosphere went completely unnoticed until it disappeared from our sight. If this seems as disturbing and fascinating to you as it does to me, consider supporting and subscribing to stay updated on these cosmic close encounters and the mystery we are unraveling. Write in the comments where you are listening from, what time it is for you, and do you think we should worry more or admire how much we still miss in the night sky? And if you want to help our community grow, share these videos on social media. Thank you for your support. The asteroid, ranging from 1 to 3 meters in size, was too small to pose a danger to cities or civilizations. If he had truly entered the atmosphere, he would have burned up, turning into a bright fireball. However, this is exactly what keeps astronomers awake at night. If we cannot reliably detect objects of such size moving at a speed that allows them to cover the distance from New York to Los Angeles in less than a minute, what else might we miss? The European Space Agency and NASA monitor thousands of objects near Earth, meticulously cataloging those that pose the greatest collision threat. To be classified as potentially hazardous, an asteroid must have a diameter of at least 140 meters and follow an orbit that brings it within at least 7.5 million kilometers from Earth, which is about 20 times the distance from us to the Moon. Asteroid 2025 TF is significantly smaller than this threshold, which partly explains why it went unnoticed. Our telescopes and observation systems are focused on detecting large objects that could lead to catastrophic consequences and a new mass extinction if they collide at the wrong angle. But this tiny guest reminds us that space is not empty. It is full of fragments, ancient pieces formed during the creation of our solar system, remnants of shattered worlds that never became planets, leftovers from collisions that occurred when the Earth was still young. Most of these materials remain far away, locked in stable orbits between Mars and Jupiter, or drifting in the distant Kuiper Belt beyond Neptune. However, gravitational interactions, the subtle pulls of the massive Jupiter, or the push from a passing comet, can alter these orbits, sending rocks on new trajectories that sometimes intersect with ours. What does asteroid 2025 TF do? What is particularly interesting is not only that he approached closely, but also that it happened in a month when the sky seems unusually busy with visitors. A bright traveler. While one space traveler passes by unnoticed, another makes a much more spectacular entrance. The comet C2025A6, better known as Lemon after the observatory that discovered it, begins to glow brighter in our October sky. Amateur astronomers around the world capture increasingly impressive images as this ancient ball of ice and dust approaches Earth. Unlike the secretive asteroid that surprised us, Lemon has been carefully monitored since its discovery and is now on the verge of being visible to the naked eye. Over the next few weeks, if the conditions are right and the sky is dark enough, you will be able to go outside and see it yourself. A faint spot of light with a ghostly tail stretching from the sun. Comets are fundamentally different from asteroids. Asteroids are rocky or metallic, solid pieces of material that formed in the warmer inner part of the solar system, while comets are icy bodies that originated in cold, distant regions. Sometimes comets are called dirty snowballs, although this name does not fully reflect their true nature. The core of a comet consists of frozen water, carbon dioxide, methane, and ammonia, mixed with dust and organic compounds, the chemical components of life. As the comet approaches the sun, solar radiation heats its surface, causing ice to sublimate, turning into gas without passing through a liquid phase. This creates a comet, a temporary atmosphere of gas and dust that can stretch for hundreds of thousands of kilometers. Solar wind and radiation pressure push this material away from the core, forming a characteristic tail that always points away from the sun, regardless of the comet's direction. Comet Lemon is not the only one delighting us this month. Another guest, Comet C2025 R2, known as the Swan, will fly past Earth at the end of October at a distance of 0.26 astronomical units, close enough for viewers with binoculars or small telescopes to enjoy its spectacle. Both comets are currently shining at about 6th magnitude, on the edge of visibility to the human eye under ideal conditions. However, comets are known for their unpredictability. They can suddenly shine brightly if their rotation exposes fresh ice to sunlight, or if an eruption sends a cloud of material into space. Comets can also fragment, breaking apart under the influence of solar heating or tidal forces, creating multiple nuclei, each developing its own comet and tail. What attracts people to observe comets, besides their beauty, is their connection to ancient times. The ice in these objects formed billions of years ago in remote corners of the solar system, preserved in a cosmic freezer far from the sun's warmth. When we see a comet, we observe material that existed before oceans appeared on Earth, before the moon fully formed, before life emerged in warm tidal pools or deep-sea vents where self-replicating chemistry first arose. Some scientists believe that comets delivered significant amounts of water to early Earth, crashing into it in a bombardment that helped fill our oceans. Others believe that organic molecules found in comets, including amino acids, the building blocks of proteins, could have provided our planet with the essential materials for the beginning of life. This connection between ancient comets and the origin of life leads us to another discovery that makes scientists reconsider how widespread the ingredients for life are in the universe. Chapter 3. Nursery for the Moon. 625 light-years from Earth, something remarkable is happening around a young planet. The James Webb Telescope has captured the first direct measurements of the disk where a moon is forming, surrounded by rotating rings of gas and dust encircling the exoplanet called CT-KRB. And inside this disk, Webb discovered chemical signatures that could lead to the formation of moons: hydrogen cyanide, acetylene, benzene, propylene, ethane, carbon dioxide. All these carbon-rich molecules swirl in a structure that seems familiar to planetary scientists studying the history of our solar system. This is important because for decades we have proposed theories about how moons are formed, but we have never observed this process in action. The 4 largest moons of Jupiter, the Galilean satellites, discovered by Galileo in 1610, orbit their planet in a flat plane, indicating that they formed from a disk of material surrounding Jupiter billions of years ago, similar to how planets formed from the disk around the young sun. 2 of the most distant moons, Ganymede and Callisto, are 50% composed of water ice, although they likely have rocky cores of carbon or silicon beneath their frozen shells. Assessing their orbits and composition, scientists long suspected that a disk once existed around Jupiter, where raw materials gathered and coalesced to form moons. Now, thanks to the CT-KRB system, we can observe such a process in real time, although it should be remembered that, in an astronomical sense, real time is a somewhat deceptive concept. The light we register from this system left it 625 years ago, when Earth was in the midst of the Renaissance, and no one could yet imagine planets beyond our solar system. From our perspective, we witnessed the formation of the moon during this process, and the details are captivating. The planet spins around a star that is only 2 million years old, continuing to gather material from its surrounding disk. This means we are observing a system in its early stages of development, a planetary nursery where multiple generations of structure formation are occurring simultaneously. Researchers were most surprised by the sharp chemical difference between the disk forming the moon and the disk forming the planet. The surrounding disk around CT-KRB is rich in carbon-containing molecules but lacks water. Meanwhile, the surrounding disk around the star contains water, but is devoid of the carbon chemistry typical of a planetary disk. This chemical segregation occurred in just 2 million years, indicating that the chemistry of the disk changes rapidly and follows different paths depending on local conditions. Temperature, radiation levels, and the presence of magnetic fields all affect which molecules can survive and which are destroyed. The consequences of this research go beyond understanding moon formation. If we can map the chemistry of these disks in young systems, we can start predicting which exoplanets might have moons and which of these moons could have conditions suitable for life. In our solar system, some of the most promising places to search for life are not planets, but moons. Europa, orbiting Jupiter, likely has an ocean of liquid water beneath its icy crust, kept warm by tidal heating from Jupiter's gravitational pull. Enceladus, a small moon of Saturn, ejects jets of liquid water into space from an underground ocean, and scientists have discovered organic molecules in these jets. If moons around other stars form with similar characteristics, the number of potentially habitable worlds in the galaxy significantly increases. We will need to pay attention not only to planets in the habitable zone, around their stars, but also to the moons of giant planets in any system. This expanding notion of where life might arise is connected to the technologies we are developing here on Earth, technologies that may one day help us reach these distant worlds or at least understand them better. Chapter 4. The United Nations declared the year 2025 as the International Year of Quantum Science and Technology, marking 100 years since the initial development of quantum mechanics. This is just the right time, as the year 2025 seems to be the year when quantum computing will move from mere laboratory curiosity to practical reality. In November 2024, Microsoft and Atom Computing announced that they successfully created and entangled 24 logical qubits, a technical achievement representing a significant step towards creating quantum computers capable of solving useful problems. To understand why this is important, it is necessary to discuss what makes quantum computers different from the device you are using. To listen to this text right now. Classic computers, whether smartphones or supercomputers, process information using bits, units that represent either 0 or 1, on or off, true or false. Everything your computer does, from streaming video to complex simulations, boils down to manipulating vast amounts of binary digits at incredible speeds. Quantum computers operate on fundamentally different principles. Instead of bits, they use qubits, quantum bits that can exist in a superposition of states, simultaneously representing 0 and 1 until measured. This is not just a metaphor or trick. At the quantum level, particles truly exist in multiple states simultaneously, a consequence of the wave nature of matter described by quantum mechanics. When you have several qubits in superposition, they can represent exponentially more information than the same number of classical bits. Two classical bits can represent four possible values: 0, 0, 0, 1, 1, 0, or 1, but only one of them at any moment. Two qubits in superposition can represent all four values simultaneously. Three qubits can represent 8 values at once. Scaling continues exponentially, meaning that a quantum computer with just a few hundred qubits could theoretically perform calculations that would take classical supercomputers longer than the age of the universe. However, there was always one catch. Qubits are extremely fragile. They lose their quantum properties, a process called decoherence, when interacting with the environment. Temperature fluctuations, random electromagnetic fields, even cosmic rays penetrating the laboratory can cause errors. This is why quantum computers must be cooled to temperatures near absolute zero and shielded from external influences. Even then, errors accumulate so quickly that calculations become unreliable before they are completed. The breakthrough that makes the years 12 and 13 so significant is linked to achievements in quantum error correction, the ability to detect and fix these errors without destroying the quantum state you are trying to preserve. The creation of 24 entangled logical qubits means creating qubits with built-in error correction, making them much more stable and reliable compared to the physical qubits that make up the raw material. Entanglement is another quantum phenomenon that Einstein famously called spooky action at a distance. When qubits are entangled, measuring the state of one instantly affects the state of others, regardless of the distance between them. This allows quantum computers to perform certain types of calculations, such as searching databases or factoring large numbers, much more efficiently than classical computers ever could. The race to create practical quantum computers now has a global and intensely competitive nature. At the beginning of the 12th year, Japan announced an investment of $7.5 billion in quantum technologies. Spain allocated $900 million. These investments raised the total amount of government funding for quantum research above $10 billion. This signals that governments view quantum computing not just as a scientific curiosity, but as a strategic technology capable of transforming everything from drug discovery to cryptography and artificial intelligence. The private sector is also actively involved. Companies like Google, IBM, and Amazon continue to push the boundaries of possibility. Google claims its quantum processes can solve certain tasks many times faster than classical supercomputers. IBM has developed a roadmap for creating a system with 200 logical qubits by the year 28. Meanwhile, startups are exploring alternative approaches using photons instead of superconducting circuits or trapped ions instead of solid-state devices, each with its own advantages and complexities. But besides engineering achievements, there is something almost philosophical in quantum computing that captures the imagination. These machines operate according to principles that contradict our everyday intuition about how reality is structured, and yet these principles seem to be fundamental to the universe itself. The same quantum mechanics that enables qubits also governs the behavior of atoms, the structure of molecules, and the light emitted from stars. In a sense, quantum computers allow us to use the universe's native language to solve problems that would otherwise remain unsolvable. One of these problems is understanding and controlling the process of nuclear fusion, which leads us to a series of breakthroughs that occurred during the same period. Chapter 5. Catch the Stars. On February 12, 2025, scientists at the West Tokamak reactor in France set a new world record by maintaining a hot plasma state for 22 minutes and 17 seconds. Surpassing the previous record by more than 4 minutes. plasma reached a temperature of 50 million degrees Celsius, which is about 3 times higher than the temperature at the center of the sun. This may seem like insignificant progress to those unfamiliar with nuclear fusion research. Ultimately, the sun has supported synthesis reactions for 4.5 billion years without human intervention, but creating and controlling a process similar to stars on Earth is one of the most challenging tasks in science and engineering. Nuclear fusion occurs when atomic nuclei are pressed together with such force that they overcome their natural electromagnetic repulsion and merge, releasing energy in the process. This occurs on the sun due to the immense mass of the star, creating colossal gravitational pressure in its core, along with temperatures of 15 million degrees. On Earth, we do not have such a gravitational advantage, so we need even higher temperatures to achieve synthesis, as well as a way to hold plasma at such high temperatures without allowing it to touch any physical surface, as no material can withstand such temperatures without instantly vaporizing. The solution lies in magnetic confinement. The tokamak uses powerful magnetic fields to create a force cell that holds plasma in the shape of a torus, suspended in a vacuum, not touching the walls. Achieving 22 minutes in Western reactors is significant, as future thermonuclear power plants will need to operate continuously rather than in short bursts. It is economically impossible to generate electricity if your reactor must constantly shut down and restart every few minutes. This record demonstrates that engineering tasks related to continuous operation, managing heat flows, and maintaining plasma stability against instabilities that could disrupt magnetic confinement are gradually being solved. The previous record, just over 17 minutes, belonged to the Chinese reactor Eastern Tokamak and was set in January 2025, indicating that we witnessed 2 key milestones in plasma duration within just a few weeks. These are not the only breakthroughs in nuclear fusion currently occurring. ETAE Technologies, a private company in the field of nuclear fusion, announced in April 2025 a significant simplification of the process of forming and stabilizing its plasma. Their method uses a so-called reversed field configuration, or RFC, a magnetic structure that is more compact than a traditional tokamak. Previously, the creation of the FRC required complex shaping sections at both ends of the device, where plasma was generated, then accelerated, and collided at high speed in the center. The ETAE company found a way to generate heat and stabilize plasma at the core of its device using only neutral beams, eliminating the need for complex auxiliary equipment. This reduces costs, increases efficiency, and brings them closer to demonstrating a positive energy balance by the end of the decade. Meanwhile, the private sector of nuclear fusion is rapidly developing. Commonwealth Fusion Systems is building a prototype plant called Spark near Boston, which is set to start operations in 2027. The Helion company completed the initial tests of its new device designed to achieve break-even using a different magnetic compression scheme. General Fusion, located in Canada, is developing a demonstration system that uses a completely different approach: mechanical compression of plasma, rather than relying entirely on magnetic fields. The variety of methods reflects both the complexity of the problem and the understanding that there are multiple paths to successful nuclear fusion energy. In December 2022, scientists at the National Ignition Facility achieved nuclear fusion for the first time, producing more energy than the lasers used to initiate it. This became a scientific milestone, proving that controlled thermonuclear fusion is physically possible. But transforming this conceptual proof into an energy facility requires solving many engineering challenges. Fuel for synthesis, usually a mixture of deuterium and tritium, isotopes of hydrogen, must be supplied continuously. Neutrons generated by thermonuclear reactions carry enormous energy and make the reactor walls radioactive, so materials must withstand years of neutron irradiation without degradation. Generated heat must be efficiently utilized and converted into electricity, and all of this should occur at a cost comparable to other energy sources. The appeal of nuclear fusion, despite all its challenges, lies in the promise of nearly limitless clean energy. Deuterium can be extracted from seawater, where it naturally occurs at a rate of 1 atom for every 6,500 hydrogen atoms. At such concentration, the oceans contain enough deuterium to power human civilization for millions of years. Tritium is rarer and must be obtained from lithium, but lithium is relatively accessible. Nuclear fusion does not produce long-lived radioactive waste, unlike fission reactors. It does not emit carbon, and the fusion reactor cannot melt down or explode because the plasma is so rarefied that any disturbance leads to an immediate cessation of the reaction. The question now is not whether nuclear fusion will work, but when it will become practical and economically viable. Experts point to rapid progress in both public and private projects, suggesting we may see the first commercial fusion energy in the grid as early as the early 2030s. Skeptics note that nuclear fusion has consistently been 20 years away for the last 60 years and warn that unexpected problems always arise. But in the year 2025, the situation feels different due to a combination of technological breakthroughs, massive investments, and an urgent need for clean energy sources to combat climate change. For the first time, it seems plausible that a child born today could grow up in a world where nuclear fusion energy is as common as solar panels or wind turbines. And perhaps this child's generation will use thermonuclear spaceships to explore the solar system, following ancient comets and asteroids, as well as investigating planets and moons that we have only seen from afar. One of these moons, Mars, continues to amaze us with hints that it could have once been habitable. Chapter 6. Leopard Spots on Mars. In July 2024, the Perseverance rover drilled a rock sample from a stone nicknamed Cherver Falls in the Jezero crater on Mars. This breed demonstrated features that the mission scientists described as the most mysterious, complex, and potentially significant they had ever encountered. After a year of rigorous scrutiny, the data was published in the journal Nature in September 2025 and represents the most compelling evidence that microbial life may have once existed on Mars. The key word here is could, because one of the most difficult lessons of astrobiology is that nothing is as simple as it seems at first glance. Cherver Falls is located in an ancient riverbed in the area that Perseverance is exploring, called Bright Angel. Billions of years ago, water flowed through this area, carving channels until it rushed into the Jezero crater, which was a lake at the time. The stone itself is sedimentary rock made of clay and silt. This material on Earth preserves fossil remains and chemical traces of ancient life. The Perseverance tools revealed organic carbon, sulfur, oxidized iron, and phosphorus, a combination that often indicates biological activity on Earth. But what truly caught the scientists' attention were small formations they called leopard spots. Tiny specks enriched with iron phosphate and iron sulfide are scattered across the stone like spots on an animal's fur. On Earth, when microorganisms process organic matter, they often produce iron phosphate and iron sulfide as metabolic byproducts. However, the structure of these connections in Cherver Falls resembles what we see in rocks containing fossilized microbial communities. And here's the problem. Chemical reactions can also create similar patterns without the involvement of biology. Hydrothermal processes, volcanic activity, meteorite impacts, all of these can generate iron-rich minerals. The task is to distinguish biological and non-biological sources based solely on chemistry and texture, especially when doing so remotely with tools on a rover millions of kilometers from Earth. This uncertainty is the reason why scientists use the term potential biosignature instead of stating that they have found evidence of life. A potential biosignature is a substance or structure that may have a biological origin but requires further data or study before any conclusions can be drawn. This approach is prudent, as the claim that we have found evidence of extraterrestrial life, even if it concerns only extinct microbes, is unusual and requires unusual proof. The scientific community learned this lesson from past disputes, such as the 1996 announcement that a meteorite from Mars found in Antarctica contained possible fossilized bacteria, which subsequent studies could neither confirm nor deny. Special interest in the findings at Cherver Falls is due to the age of the stones. The formation of Bright Angel is relatively young from a geological perspective, younger than many ancient stones studied by Perseverance. It was previously hypothesized that signs of ancient life would be limited to the oldest stones formed when Mars had a thicker atmosphere and liquid water on its surface. The discovered potential biosignatures in younger rocks suggest that Mars may have remained habitable longer than previously thought, or that conditions favorable to life returned in later periods. Perhaps volcanic activity periodically warmed the planet, melting underground ice and creating temporary bodies of water where life could survive. The specimen, officially named the Sapphire Canyon after the waterfall in the Grand Canyon, is now one of 30 specimens collected and stored in sealed titanium tubes. These samples represent a slice of Martian geology, rocks from various eras and conditions, each selected for potential clues about Mars's past. The ultimate goal is to return these samples to Earth as part of a Mars sample return mission. Despite significant technical and budgetary challenges of this mission, the return of samples would allow scientists to analyze them with tools far more advanced than those that can be sent to Mars, capable of measuring isotope ratios, searching for amino acids, and examining mineral structures at the atomic level. Until then, the sample from Sapphire Canyon remains in the depths of Perseverance, representing a tiny piece of Mars that could become the most important discovery in astrobiology or merely interesting geology. The uncertainty brings both disappointment and excitement. We live in an era when the question of whether life exists beyond Earth may finally receive an answer, not through speculation, but through direct observation. Will this answer be received from Mars, the icy moons of Jupiter and Saturn, or through spectroscopic analysis of exoplanet atmospheres? The search is moving faster than ever, driven by technologies that didn't exist a generation ago. Some of these technologies, especially in the field of artificial intelligence, are developing so rapidly that they simultaneously change several areas. Chapter 7. In 2020, an average company spent $1,900,000 on generative artificial intelligence initiatives, yet less than 30% of AI leaders reported that their CEOs were satisfied with the return on investment. This rupture highlights an important point about the current state of the revolution in artificial intelligence. The technology does work, sometimes even with stunning results, but transforming this capability into business value proves to be more complex than initially thought. The year 2025 became a time to rethink approaches, urging companies to move from experiments to targeted implementation, from questions about what artificial intelligence can do to questions about what problems it can solve better than existing methods. The technologies continue to develop at an astonishing pace. In September 2025, researchers at Microsoft announced a breakthrough in protein simulation using an AI-based system called A2BMD. Proteins are molecular machines of life, folding into complex three-dimensional shapes that define their functions. Understanding how proteins fold and interact is crucial for drug discovery, enzyme engineering, and understanding diseases. However, simulating protein dynamics has always been a computationally intensive task, as proteins are large molecules with thousands of atoms, and their behavior depends on quantum mechanical interactions at the smallest scales. AI2BMD allows researchers to simulate this dynamics with unprecedented speed and accuracy, which can accelerate the discovery of new drugs and therapies. This is not the only way in which artificial intelligence is transforming science. In neurobiology, an AI model called Cell Transformer, developed by researchers from the University of California, San Francisco, and the Allen Institute, created one of the most detailed maps of a mouse brain ever produced, identifying 1,300 regions and subregions, including previously unexplored areas. The model works by analyzing vast datasets of spatial transcriptomic data, essentially matching which genes are active in which cells and where those cells are located. This allows AI to identify patterns and boundaries that may escape human researchers' attention, demonstrating brain organization at a level of detail that would be impossible to achieve manually over decades. The same AI methods can be applied to other organs and tissues, including cancer tumors, opening new avenues for understanding diseases and developing treatments. Another breakthrough in artificial intelligence came from University College London, where researchers developed an algorithm capable of identifying different types of brain cells by their electrical signals with 95% accuracy. For decades, neurobiologists could record the electrical activity of neurons, but could not determine the type of neurons they were receiving signals from without genetic markers or staining methods. This new approach uses AI to recognize subtle patterns in electrical impulses produced by various types of neurons, effectively training the machine to read neural code. The consequences of using brain-computer interfaces and treating neurological disorders like epilepsy are significant. However, as researchers warn, there is still a long way to go before this becomes a practical clinical tool. Artificial intelligence not only accelerates research, but also becomes an integral part of everyday tools and workflows. In 2025, the analytical company Gartner predicts that 75% of enterprises will transition from pilot artificial intelligence projects to full-scale operations, leading to significant expansion of data and analytics infrastructure. Artificial agents, autonomous or semi-autonomous software entities capable of perceiving their environment, making decisions, and acting, are gradually transforming from concept to reality. They are not the 5-year-old chatbots limited to pre-written responses. These systems are capable of performing complex tasks such as analyzing legal contracts, managing supply chains, writing and debugging code, as well as providing personalized medical recommendations. The rise of artificial agents raises questions that go beyond technology. If an artificial agent makes a mistake that causes harm, who is responsible? The developer, the company implementing it, or the user who relied on it? At the end of 2025, a lawsuit was filed in Colorado, raising questions when parents claimed that an AI chatbot contributed to their teenager's suicide by modeling emotionally manipulative conversations. This case could become emblematic in defining responsibility for artificial intelligence systems and the ethical obligations of the companies that create them. As artificial intelligence becomes more powerful and penetrates sensitive areas such as mental health, education, and personal relationships, society will need to address issues of trust, accountability, and proper boundaries for AI. There is also the question of how artificial intelligence itself will evolve. Current large language models are trained on vast amounts of text collected from the internet, learning language patterns that allow them to generate coherent and often useful responses. But they do not understand what they are saying in a deep sense. They lack common sense, make factual errors, can be deceived by hostile inputs, and sometimes produce confident but completely incorrect results, which is called hallucination. The next generation of artificial intelligence systems will have to overcome these limitations by implementing better logical reasoning, the ability to verify their results, and perhaps some form of understanding that goes beyond mere pattern matching. Some researchers believe that the way forward lies in a combination of different types of artificial intelligence, known as composite artificial intelligence. Instead of relying on a single large model, systems are created that integrate several specialized models, each excelling in a specific task, along with traditional software and databases. Some experts believe that a breakthrough in artificial intelligence will occur due to improved training methods or closer integration of AI with robotics, giving it a body and sensory feedback to understand the physical world like humans do. There is also growing interest in neuromorphic computing, creating chips that mimic the structure of biological brains and may offer more efficient and capable solutions than existing approaches. No matter what path artificial intelligence chooses, it is clear that we are still in the early stages of understanding what this technology can and cannot do, and what it means for society. Excitement is justified, the potential is real, but there are also challenges and risks. As we create more powerful AI, we need to develop wisdom for its responsible use. This same need for wisdom pertains to another area where our fundamental understanding of reality may change: the mysterious components that seem to make up much of the universe. Illusion of darkness. For almost a century, cosmologists believed that the universe mainly consists of things we cannot see. Ordinary matter, which makes up stars, planets, and people, accounts for only about 5% of the total mass of the universe's energy. Another 27% is dark matter, invisible but detectable through its gravitational effects on galaxies. The remaining 68% is dark energy, an even more mysterious force that seemingly accelerates the expansion of the universe. Together, dark matter and dark energy dominate the cosmic budget, shaping the structure and fate of all existence. But what if they don't exist at all? In October 2025, physicist Rajendra Gupta from Ottawa proposed a radical alternative. Instead of filling the universe with invisible particles and unexplainable energies, Gupta suggests that fundamental forces of nature, like gravity, slowly weaken as the universe ages. If this is true, then the phenomena we attribute to dark matter and dark energy may be illusions, artifacts of using constant laws of physics to describe a universe where these laws gradually change. The idea is both simple and profound. We assume that the force of gravity today is the same as it was a billion years ago and will remain so in a billion years. But what if this assumption is wrong? What if gravitational pull was slightly stronger in the past and will become slightly weaker in the future? Such a change could make distant galaxies spin faster than we expect based solely on visible matter, mimicking the effect of dark matter. It could also make the expansion of the universe seem to accelerate over time, simulating dark energy. This model does not require exotic invisible substances. It is enough to have temporal constants, a universe where rules gradually change, a space that evolves on its own. This is not the first time someone has suggested changing our laws of physics to eliminate the need for dark matter and dark energy. Modified Newtonian dynamics, or MOND, has existed for several decades and can successfully explain the rotation curves of galaxies without invoking dark matter. However, MOND struggles to explain observations on larger scales, such as the behavior of galaxy clusters or the patterns we see in the cosmic microwave background, the afterglow of the Big Bang. Gupta's approach, which he calls CC plus TL, attempts to provide a unified explanation for both cosmological scales, where dark energy appears to act, and astrophysical scales, where dark matter seems necessary. By introducing a parameter that changes over time and depends on the local density of matter, it can reproduce the observed rotation curves of galaxies and the accelerated expansion of the universe without adding new substances. Interestingly, the timing of this proposal coincides with other observational data, indicating possible issues with our standard cosmological model. Data obtained using a spectroscopic instrument to study dark energy, published in April 2025, suggests that dark energy may not be constant. Instead, it may weaken over time, changing in a way that the standard model cannot easily explain. If dark energy changes, we need to reconsider our theories, and once you start revising, it's worth asking whether dark energy exists in the form we understand it. Meanwhile, experiments to search for dark matter particles continue to yield no results. The Lux-Zeppelin detector, the most sensitive dark matter detector ever created, has been operational for several years and has found nothing. It has set strict limits on the properties that dark matter particles must have if they exist, gradually excluding vast areas of theoretical possibilities. Each absence of results makes the remaining possibilities of what could be dark matter more exotic and less likely. Some physicists begin to wonder if we are searching for something that does not exist, like ancient astronomers adding more and more epicenters to justify the geocentric model of the solar system. However, it is not so easy to give up dark matter and dark energy, as they explain so much. They explain why galaxies rotate the way they do, why clusters of galaxies maintain their integrity, why gravitational lensing occurs where it does, and why the cosmic microwave background has observable patterns of hot and cold spots. Any alternative theory must explain all these phenomena at least as well as dark matter and dark energy, or preferably even better. The Gupta model is a step in this direction, but it must undergo rigorous tests to conform to all cosmological data before it can be considered a serious competitor to the standard model. What makes this debate so fascinating is its connection to the most fundamental questions in science. How can we know what is real? Dark matter and dark energy have never been directly detected. We assume their existence based on gravitational effects, the movement of visible matter, and the structure of spacetime. But conclusions can be deceptive. For centuries, astronomers believed that planets moved in perfect circles because circles were considered the most perfect shape. The truth was that planets move in ellipses, a simpler solution if we stop assuming perfection. Can we make a similar mistake now, assuming the existence of exotic substances in the universe when our equations actually need adjustment? The response will come with new and more accurate data. The Versace-Rubin Observatory, which will begin observations in late 2025 or early 2026, will explore the sky using the largest digital camera ever created, capturing billions of galaxies with unprecedented detail. The data she collected will test dark matter and dark energy models with an accuracy unattainable by current experiments. Similarly, the Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will measure the expansion rate of the universe and map the distribution of matter on cosmic scales. Over the next few years, new tools and ongoing experiments should clarify whether dark matter and dark energy are real, or if we need to fundamentally rethink cosmology. In any case, this process reveals something beautiful about science. It is never complete. Every answer gives rise to new questions. Every certainty ultimately faces a challenge. And sometimes the most revolutionary discoveries come not from finding something new, but from realizing that what we thought we knew was incomplete. Chapter 9. While scientists discuss the nature of space and engineers build quantum computers and fusion reactors, a quiet revolution is happening in how we leave Earth's atmosphere. In October 2025, Blue Origin conducted its 15th tourist spaceflight. Passengers aboard experienced several minutes of weightlessness, saw the curvature of the Earth against the blackness of space, and safely returned to Earth. For them, it was probably a transformative experience, the perspective shift that astronauts call the overview effect. For the space industry, it was just another successful flight in what is becoming a routine commercial operation. The normalization of access to space seems significant when looking at the bigger picture. A generation ago, space flights were the exclusive prerogative of government agencies and professional astronauts, people who underwent years of training and strict selection. Now private companies send paying clients, and although the price is still exorbitantly high for most, costs are decreasing as technology improves and competition increases. SpaceX revolutionized launches with reusable rockets, significantly reducing the cost of sending payloads into orbit. Blue Origin is developing its own reuse systems. Other companies are creating spaceplanes, orbital hotels, lunar landing modules, and concepts for missions to Mars. The infrastructure being built today is not just for tourism. It lays the groundwork for a future where humanity becomes a multiplanetary species. Starship from SpaceX, the largest and most powerful rocket ever built, designed for transporting cargo and, in the future, people to the Moon and Mars. NASA's Artemis program plans to return astronauts to the Moon's surface, establishing a sustainable presence to test technologies needed for longer missions. China is building its space station and has announced plans for a lunar base. India, Japan, and several European countries are developing their own space capabilities. All this activity raises questions about what we will do when we reach these places. Space is an unforgiving environment. There is no air, no water, extreme temperature fluctuations, and radiation from the sun and cosmic rays. Building habitable habitats that can support human life will require solving problems in life support, agriculture, production, and medicine. We will need to extract resources from asteroids, the Moon, or Mars itself, as launching everything from Earth is impractical for long-term colonization. We will need energy sources, probably solar panels supplemented by small nuclear reactors, and we will have to address the psychological issues of isolation, confinement, and being far from Earth. But perhaps the most important question is why we need this. Practical answers include resource extraction, scientific discoveries, and ensuring the long-term survival of humanity by spreading beyond a single planet vulnerable to asteroid impacts, supervolcanoes, and other existential threats. More ambitious answers point to human curiosity and the drive to explore. The same impulse that sent our ancestors out of Africa to all continents, encouraging explorers to cross oceans and scientists to delve deeper into the mysteries of nature. Space is a final frontier, not because it is empty, but because it is vast and largely unexplored, full of possibilities we can barely imagine. And the exploration of space does not happen in isolation from the science and technology we have discussed. Quantum computers may one day optimize spacecraft trajectories or enable new forms of communication over interplanetary distances. Fusion reactors could provide power for fast engine systems that reduce travel time to Mars from months to weeks. Artificial intelligence will be necessary for managing the complexity of life support systems, autonomous navigation, and analyzing vast amounts of data collected by sensors. The search for biosignatures on Mars or the moons of Jupiter influences how we think about where and how to search for life beyond Earth. Everything is interconnected. The universe consists not of isolated parts, but of interconnections, patterns that repeat on different scales, principles applicable in various fields. The chemistry of a comet tells us about planet formation. The behavior of a quantum computer reveals fundamental truths about reality. A thermonuclear fusion reactor simulates processes occurring in stars. Artificial intelligence mapping the brain demonstrates how complexity arises from simple rules, while a private space company makes the idea of humanity becoming citizens of the solar system more tangible, rather than just inhabitants of one planet. These connections are important because they remind us that progress is not linear. It does not occur in one area at a time, neatly divided into sectors. It happens through the mutual enrichment of ideas, when concepts developed in one context find unexpected applications in another. This happens thanks to teams of people from different disciplines working together on tasks that are too complex to solve from a single perspective. Breakthroughs in quantum computing, thermonuclear energy, Mars exploration, artificial intelligence, cosmology, neuroscience, and access to space in the year 2025 are not separate stories. They are chapters in a broader narrative about human potential and curiosity. Chapter 10: Horizon. We began with an asteroid unnoticed in the night sky and a comet brightly shining in the October sky. These two phenomena remind us that the universe is dynamic and our place in it is both small and significant. We observed how moons were forming on a distant planet from a disk of gas and dust, a process that reflects how our own moon appeared in Earth's orbit billions of years ago. We saw how quantum computers reached a level of complexity where they could soon solve problems inaccessible to classical computing, and how thermonuclear reactors sustain plasma long enough to hint at a future based on the same reactions that ignite stars. We studied a stone on Mars that may contain evidence that life once existed beyond Earth, although this question remains open and likely will until we can analyze this sample in laboratories here at home. We observed how artificial intelligence maps the brain, models proteins, and raises new questions about free will, responsibility, and what it means to be intelligent. We considered proposals that dark matter and dark energy, invisible substances believed to dominate the cosmos, may not exist at all, and that the universe we think we know might be based on incomplete equations. We noted that space travel is quietly becoming more accessible. While it hasn't become commonplace yet, the process is moving in that direction step by step. Each of these achievements carries uncertainty. Quantum computers may face unexpected obstacles that delay their practical implementation. Fusion reactors could be more complex to commercialize than optimists hope. Biosignatures on Mars might turn out to be geological rather than biological. Artificial intelligence may reach a plateau or require breakthroughs we have yet to consider. Alternative cosmologies may not explain observations as well as dark matter and dark energy, and space exploration may remain expensive and dangerous, accessible only to governments and billionaires, not ordinary people. However, uncertainty is not the same as uselessness. It is a space where discoveries happen, where our understanding expands, where we test ideas in practice and adjust them if they do not meet expectations. Science is not just a collection of facts, but a process of asking questions and refining answers, with the questions we ask now being some of the deepest ever posed. What is the universe made of? How did life begin? Can we harness the energy of stars? What is consciousness? Are we alone? How to ensure that the technologies we create are beneficial rather than harmful? These questions do not have simple answers, and that's okay. If they did, they wouldn't be worth asking. The value lies in the search itself, in the knowledge we gain along the way, in the technologies we invent for deeper exploration, and in how our perspective changes as we acquire new knowledge. 100 years ago, we did not know that the universe is expanding. 50 years ago, we did not yet visit Mars with rovers and did not discover planets around other stars. 25 years ago, quantum computers were laboratory curiosities, and artificial intelligence barely recognized handwritten digits. The pace of change is accelerating due to growing advancements in computing technology, materials, tools, and understanding. What will the next decade bring us? If nuclear fusion becomes commercially viable, an abundance of energy could transform civilization, lifting billions out of poverty and enabling projects that currently seem impossible. If quantum computers reach maturity, they could accelerate drug discovery, materials science, and cryptography, altering industries and geopolitics. If we confirm the presence of biosignatures on Mars or detect them in the atmosphere of an exoplanet, it will be one of the most significant discoveries in human history, proof that life is not unique to Earth. If artificial intelligence continues to develop, it could become a partner in scientific research, generating hypotheses, designing experiments, and analyzing data at levels beyond human capability. If access to space continues to democratize, the resources and knowledge of the solar system may become part of humanity's shared heritage, available to future generations in ways we can only begin to imagine. However, these possibilities also carry risks. Technologies and tools can be used for both good and harm. Quantum computers can break encryption that protects everything from bank accounts to military communications. Nuclear fusion, if used for military purposes, can lead to destruction. Artificial intelligence can amplify biases, destroy jobs, or be used in ways that diminish rather than enhance human well-being. Space exploration, if conducted carelessly, can lead to the spread of pollution, destruction of unique scientific objects, or worsening inequality. Managing these risks requires more than just technical skills. Wisdom, ethics, foresight, and the willingness to consider not only what we can do, but also what we must do, are required for making the right decisions. It is essential that diverse voices are heard in the decision-making process, ensuring transparency regarding risks and uncertainties, along with humility in recognizing the limits of our understanding. Scientists and engineers, paving new boundaries of knowledge, are acutely aware of these responsibilities. Even if in public discourse, technology is sometimes seen either as saviors or as a threat, with no possibility of finding a middle ground. In reality, the situation is much more complex. Technology itself is neither good nor bad. It amplifies human intentions and abilities. In the right hands, with the right goals, technology can solve problems, reduce suffering, and expand possibilities. In the wrong hands or with short-sighted goals, they can cause harm. The task is to create systems, institutions, and cultures aimed at primary goals and avoid secondary ones. This task concerns all of us, not just scientists and politicians. And here we are in October 2025, observing comets, reading about quantum entanglement, learning about plasma records, and potential biosignatures. The universe continues its ancient dance. Stars are born and die, galaxies collide, comets rush towards the sun, moons form from dusty disks. Life, at least on one small blue planet, has learned to look outward and ask questions, create tools that expand our senses and understanding. Dream of a future where the boundaries of possibilities are expanded beyond recognition. Thank you for joining me on this journey through recent discoveries and breakthroughs. If you enjoyed this exploration, consider leaving a like and subscribing to stay connected as science continues to reveal the secrets of the universe. The work to understand our cosmos never stops, and every answer found opens doors to new mysteries waiting beyond the horizon. As always, all information presented here is intended for educational purposes and is based on current research and understanding, which continue to evolve. Keep looking up, ask questions, and remember that we are all part of this great unfolding story. Until next time, wherever you may listen and whatever the time may be, good night.